Thank you very much for the introduction, and good afternoon. Welcome all, and to all in the Eurocontrol office and the ones joining from home. Thank you for tuning in, and of course a special thanks to the organization and the host of today, Yunzi, also my supervisor. And in this presentation, I would like to share you an overview of a part of the work I've done over the last year. So let's start with the problem statement. As probably many of you know, ADSB has brought us many good things. For example, a beautiful research area and the conference we are all joining today. However, next to a long list of advantages, ADSB still lacks the necessary inherent integrity verification mechanisms, which makes the system vulnerable to a number of radio frequency attacks by malicious parties. If you read in the literature, a lot of vulnerabilities and possible mitigation techniques are proposed. However, to become part of the ADSB protocol and global standard, these techniques are yet to prove their effectiveness. And many of the proposed solutions require changes in the hardware and protocol, entailing pretty high costs. So our goal in this research was to mitigate some of the security drawbacks of the ADSB protocol at low cost, and we have chosen to do this by exploring the characteristics of coherent low-level signals. Also interesting is due to a limited time schedule, we chose to focus our research on the mitigation of malicious message injection, also known as spoofing, which is considered as one of the hardest ADSB attacks to detect. So based on this problem statement and a literature study, a research proposal was defined, and the main research objective was to suggest a possible and cost-effective solution which improves the security and integrity of raw ADSB signals by designing a tool which can verify and validate the low-level signal. We have chosen to use a bearing direction of arrival of the incoming signal for integrity verification purposes. So we first developed two methods in which the direction of arrival can be independently determined using a multi-channel coherent ADSB receiver. And more specifically, the direction of arrival can be calculated based on the position information claimed by the aircraft, as well from multi-channel raw signals. So to show you a quick overview of the concept proposed, we're using a low-cost software-defined radio. Both incoming and real, real and maliciously injected ADSB signals can be received, and these signals are stored by 4 channels in the software-defined radio. And from this data, the individual ADSB messages can be found and decoded. Like I said, for each incoming signal, 2 uncorrelated values of the direction of arrival in degrees can be determined. And those 2 values can be used in a comparative analysis via a simple method for reliability classification implemented to calculate a confidence rate for each signal to validate the claimed position. Additionally, an experimental demonstration has been done with different antenna setups and different types of estimation algorithms in order to identify dynamically injected malicious ADSB signals, and of course to validate the performance of the chosen method and the developed validation and verification model. Let me first walk you through the data handling and the used hardware for the experimental demonstration. Before we go more into detail about the proposed model, just to get an idea of what the coherent receiver does. So there's chosen to make use of the Othernet's Kibero SDR board, which is a multi-channel receiver enabling multiple new options for data handling. And it allows actually receiving of ADSB signals at 1090 megahertz on 4 channels with a synchronized clock. Which again allows the direction of arrival based on phase properties. The advantages of the software-defined radio are, first of all, that it's actually really low cost and even more easy to configure. And as you can see, it's quite user-friendly. So during the lockdown, I placed it on the roof of my apartment, as you can see on your right-hand side. In this study, I used the 4-channel receiver in combination with 2 antenna setups, of 2 different antenna setups. which can be seen here on this slide. So here on your left-hand side, there's an example of the uniform circular array setup containing 4 omnidirectional antennas placed in a circular setup. And this setup can be used for 3-dimensional direction of arrival estimation with a resolution of 360 degrees. And on your right-hand side, you can see the uniform linear array setup containing 4 omnidirectional antennas placed in a straight line, both in a equidistant manner. However, the linear array can only be used for 1-dimensional direction of arrival estimation. So there's assumed that the signal comes over the horizon, and therefore there can be expected that the linear setup will not work properly for aircraft in the nearby vicinity. Another interesting thing to say is to avoid ambiguities, because you're looking at phase shift. The inter-element spacing, so the distance between the antennas, is set to 1/3 of the wavelength. Furthermore, to get a true-to-life scenario of malicious injection, we use a LIME SDR, single channel transceiver. And for the injection, a sample of real ADS-B signal is received, and using software retransmitted at a different frequency. In this case, it is 868 megahertz, since it's not allowed to broadcast signals at 1090 megahertz by law, actually, so governmental regulation. And the choice for this frequency is actually simple because it's open to use. And since the direction of arrival algorithms are based on actually the phase properties of the signal, the different frequency shouldn't have a big impact on the results, actually. Another interesting note is that since the inter-element spacing is a fraction of the wavelength, the spacing is corrected for the different frequency, of course. So now we'll walk you through the model description and the corresponding theoretical content. And the knowledge body consists actually on 6 blocks, which I discuss more into detail in the next slides. But just to make it more clear, please note the distinction between the direction of arrival calculation and the direction of arrival estimation. So it actually all starts using the Kibera SDR, and receiving the signal, an IQ data set can be generated containing the 4-channel raw signal. And here I and Q are the in-phase components of the incoming signal. And here on the screen, you can see an amplitude plot and a phase plot, just as an example to visualize what you receive. That's it for this slide. So having this information, I implemented the PyMode-S library in Python. And so from here, the information from the signals can be decoded. And on this slide on your left-hand side, you can see a list of the incoming signals. And there stands out that not every signal contains position information. So in order to fill those empty spots, a method called Kinematic Interpolation has been applied. And this method incorporates actually the object kinematics, such as the velocity and the acceleration, to have a more precise flight path. So with the now known position information of both the receiver and the transmitter, a value of the angle of arrival can be calculated. And this provides us the first one of the 2 independently determined values for the direction of arrival. And in order to find the second uncorrelated value of the direction of arrival, the properties of the coherent multi-channel receiver using 5 different algorithms are used. And for the calculation, knowledge is required about the spatial direction, the signal gain, and the expected phase relationships. And those are stored in the so-called spatial correlation matrix and the steering matrix. Here you see a quick overview of the 5 applied algorithms in order to get the estimated value for the direction of arrival. And interesting to note here is that only the multiple signal classification method is able to estimate the direction of arrival for multiple signals arriving at the same time. And I will show you an example of the application of the Bartlett's method, which consists on the reduction of variances and between the steering matrix and the spatial correlation matrix. So the algorithm provides actually per signal per range of signal a pseudo spectrum of the amplitude versus the angle resolution. And you can see that here the angle resolution goes from 0 to 180 degrees. And if you use a maximum value argument, a value for the direction of arrival can be obtained, which in this case is around, let's say 109 or 10 degrees. So if you apply all the methods and normalize the results, for each individual incoming signal, this graph can be obtained. And note that the maximum argument will give approximately the same value for all 5 algorithms. There's always a slightly difference. So having those 2 independently determined values for the direction of arrival, a standard deviation of the error between the calculated and the estimated value can be determined. And these errors are Gaussian distributed, and the corresponding values are shown here in the slide. What can you say about it? The overall, there can be seen that the circular array setup performs much better than the linear setup. But yeah, as earlier stated, the linear array setup can only estimate the direction of arrival in 1 dimension. Which in practical circumstances is causing a lot of difficulties. And from the data sets used, the Bartlett's algorithm or method gives the most accurate results for the circular array setup. So using these standard deviations of the error, a confidence rate model earlier proposed by Mr. Montero in the literature is implemented. And a value for the confidence rate for each individual signal is obtained using the cumulative distribution function and the confidence rate function as pictured in the plot on your right-hand side here. So what does the actual results look like? I have 2 examples for you. The first one is one with the real signal received by the Cabrera SDR. And the second example is one of the maliciously injected signal received by the Cabrera SDR. And here, this is actually an example of the actual determined direction of arrival over time of a flight path of only 1 aircraft. And this is visible for all 5 implemented algorithms. And in this case, what I said, it's a real signal. So in the top row, the calculated direction of arrival based on the claim position, those are the blue dots, and the estimated direction of arrival values, those are the orange dots, are plotted against the time. And each dot, or each couple of dots, actually refers to 1 complete incoming ADS-B signal. And in the bottom row, the confidence rate for each signal is plotted. So the current confidence rate, the current confidence rate is actually the confidence rate of the final ADS-B signal. That one is pictured above the plots. And as you can see, for a real signal, this value is nearing 1. Then if you go to the second example, this is an example of the application of the different direction of arrival algorithms while being maliciously injected. And the estimated direction of arrival values move over time, as you can see. Those are the orange dots in the upper row. And while the angle based on the claim position remains constant in this case. And that follows also in the confidence rates, since it's a fake signal, that it nears 0. So using the obtained values of the confidence rates provide a conclusion on whether or not to confirm the integrity of an incoming ADS-B signal. However, misclassifications can cause wrongly verified results. So to solve this, you can look at the entire flight path instead of the individual incoming signals. And this is done by implementing a simple rolling model, multiplying the obtained values of the confidence rate, where the starting point is set at 0.5. And if the value actually exceeds the upper or lower bound, which are defined as 0 and 1, the value will be limited to this bound. And for a set of correctly incoming signals, the integrity likelihood converges to 1, as you can see here on your left-hand side. And for a maliciously injected signal, the integrity likelihood converges to 0. To summarize the work, let's go back to the objective. That was to suggest a possible and cost-effective solution which improves the security and integrity of raw ADS-B signals by designing a tool which can verify and validate the low-level signal. This study functions as a proof of concept for a cost-effective method that can identify maliciously injected ADS-B signals. And this is done by comparing two independently determined values for the direction of arrival of the incoming signal, conducting an experimental demonstration using 2 types of antenna setups and 5 different types of estimation methods shows us that the best performance are obtained using the Bartlett algorithm in combination with a circular antenna setup. And finally, we have demonstrated that the integrity of real ADS-B data can be verified dynamically using a simple rolling confidence model. So yeah, that's it actually for now. Thank you for your attention. And I think we can continue with the questionnaire.
You can indeed.